In this video, I will explain the meaning and the meaning of shear center. What is it? Using its physical meaning. Using this PDF here, and you can find this PDF in this website. I will put it later. This is my website. You can find some English books here and Turkish. There are also some Turkish books. Soft PDF, soft copy of some PDF documents. It's about civil engineering education, and I also advertise some of my printed books. This is my website. Okay, and the information given in this video cannot be found in a textbook, any civil engineering educational or application textbook. You can find this information only here. I by myself discovered what actually the shear center is. You will understand what it is. It's very enjoyable video. Let's begin. For cross sections having no vertical symmetry axis, below given formula is not valid. This formula. This is the bending, simple bending formula. For example, here we have one sample cross section which has no vertical symmetry axis. This formula can only be used for the cross sections which have vertical symmetry axis, and that's why the centroid of the cross section is located on the vertical axis, since it's the symmetry axis. This is the bending formula, and this is the normal stress developed because of bending, or the moment M. Iy is the moment of inertia about y-axis, and z is the distance of the fiber or the normal stress away from y-axis. Here, y-axis. For cross sections which has vertical symmetric axis, y-axis is also neutral axis. And since this formula cannot be used for such sections, this formula can also not be used for such sections, because this formula is derived using that formula. Here, Q is the static moment in which point or place Q, the shear flux is calculated, and V is the shear force passing from the centroid. Now, I do not mention the shear center. These two formulas are not valid for this section when shear force or the moment applies on the act on the centroid. Our second note, now step by step, I will explain what shear center is. The shear flux calculated using Q equals V times capital Q divided by moment of inertia formula due to vertical shear force has a distribution given as below. This is the shear flux. Shear flux is equal to shear stress times T. T is the thickness of the wall thickness. Okay, wall thickness. Here T, here T, here T. The distribution of shear flux is so. Okay, because of vertical and downward acting V shear force. This distribution creates a shear force and a twisting moment at the centroid of the cross section. Now you see, because of this part of shear flux and not only this part, the whole shear flux creates here its their resultant twisting moment and shear force. These two eliminates each other, but these shear flux, the resultant of these shear flux, must equal to this V shear force. But this shear flux is okay. Step by step, I will explain. However, shear flux, which is equal to shear stress times wall thickness, is the component developed only because of vertical shear force. So these shear fluxes are the components of this shear force. Or in other words, the resultant of these shear flux shall equal to only V shear force, and T must be 0. But here in this case, it is impossible that T is 0 because of the distribution of shear flux and the cross section shape. Hence, this formula cannot be used for cross sections not having vertical symmetry axis. Okay. You see, if we integrate the shear flux along this portion or along the flange of the cross section, we will get this force Ff, and from the integration of these shear fluxes, we obtain Fw, and from the integration of these shear fluxes, we obtain Ff, but in the opposite direction. In comparison to the upper flange, Ff. The resultants of Q about centroid C are X, you see. Let's use now this shape. They are equivalent. Cross section is same. And instead of shear fluxes, we use their resultant forces. Here. Two Ff we have here. They are in the opposite directions, and but their magnitude is same. Because of that, the moment caused because of Ff is 2Ff is that one everywhere in the cross section, and so also in the centroid at point C. And the moment caused by Fw at point C is that much, force times its moment time. So we have a twisting moment, and you see there is a positive sign here, so it's impossible that it is 0. And the resultant force in horizontal resultant force equals to Ff minus Ff0, that's okay. But the vertical resultant equals to Fw. So Fw shall equal to V. That's okay. But this is not okay because it's impossible that this is 0. So there is not any other way for vertical shear force acting downwards. So the shear flux has to be so distributed. Okay. But in this condition, there is a non-zero twisting moment. So we cannot use these two formulas. To be able to use that formula for cross sections having no vertical symmetry axis, an equivalent cross section having vertical symmetry axis is used. This explanation is not given in a textbook. I am giving it here now. I think some of them know this reality, but they do not mention it. But maybe some of them don't know it. So equivalent cross section is we double the cross section and we double the magnitude of shear force. In this case, this is the resultant force, no twisting moment. It acts on point D, and its component forces on the cross section is so the cross section is composed of two channels and it has vertical symmetries. And this distance from the midpoint of that wall to that midpoint of that wall is 2 times E. Now, if we write the resultant of the components, the horizontal component of the resultant force is FF minus FF plus FF minus FF, which equals to 0. And in vertical direction, 2FW it is equal to, and which has to equal to 2V shear force. And we have the same result, FW equals V, which we obtained in the real cross section here. If we calculate the resultant moment about point D, which is the centroid of the equivalent cross section, not the centroid of the real cross section. Centroid of the real cross section is C, centroid of the equivalent cross section is D. And we will soon see that shear center is actually the centroid of the equivalent cross section. So the resultant moment about point D, which is the centroid of the equivalent cross section, and actually indeed the shear center, we have FF times D, one positive from here, and minus FF times D, negative, and again one positive FW times E and one negative FW times E, and resultant moment is 0. So the resultant of the component forces or the shear flux equal to only shear force itself, that is 2V for the equivalent cross section. Here point D is the centroid of the equivalent cross section, which at the same time the shear center of the real cross section. The moment at point C can be calculated from the half of the shear force or from the components at the right hand side of the equivalent cross section. Now let's calculate the moment. Think that 2V is shared by this shape and this shape. So only 1V is acting, or 1V is resisted by this shape, and the other V force is resisted by this shape. So let's calculate the V, the moment about at point C, at the right hand side of the point, because of V, which is the half of the acting shear force. That is V times E plus F, and it shall equal to the moment, twisting moment, developed because of these forces. This is FF times D plus FW times F. Okay. From here we obtain E equals to that. So here we know the value of D, we know the value of shear force. So if we calculate the FF, which is the resultant force of the shear flux distributed on the upper flange. So the place of shear center can be calculated by this formula. Now I continue. The shear flux Q or the shear stress tau calculated using an equivalent section or real section are equal. Proof is given below. Now this is the equivalent cross section. I want to calculate the shear flux at that point. So E means equivalent. So the shear flux here QE equals to shear force VE, which is 2V, times QE, the static moment about neutral axis, y axis here. That is A prime times let's say z prime. Okay, and its moment of inertia is 2 times the moment of inertia of that one, the single one, or the real section. So here I write 2 times Ey. The two eliminate each other, and we have that one. And from the real section, the formula is here. Instead of Q, static moment, I write A prime times Z prime. And as you see, the shear flux calculated only using the non-symmetrical real section or equivalent symmetrical cross section, they both are same, equal. As a result, there is no need to draw an equivalent cross section. Solely the distance E is calculated and V is applied to point D. Then the formula of shear flux can be used. The twisting moment about point D is 0, which we proved before, if equivalent or real cross section is used. The place of D can be found using this condition. The condition of finding the place of shear center is the twisting moment about that point must be 0. So let's calculate. Here, moment at that point is equal to Ff times D minus Fw times E, as you see from here. Ff times D, where can we see it? Using only one section, Ff times, I didn't draw it. Yeah, here you can see it. Assume, understand, Ff is here in this direction, Ff is here in this direction, Fw here in vertical, and it acts downwards. And then the moment of resultant forces Ff and Fs and Fws provides me the moment about point D with this expression. If I replace instead of Fw V, I proved that Fw equals to V in the previous pages. And if I substitute the value of E, this is the place of shear center. If I substitute its value here, the result was found here. As you see, moment about point D, which is the shear center, is 0. For any cross section, shear center or point D is the point about which the twisting moment is 0. So no one need to draw the equivalent cross section to find the place of shear center. Using this condition, the place of shear center is found, and this information is provided in all textbooks. But none of the textbook explains from where this idea comes from. None of them tells us the equivalent cross section. That's why intelligent and clever people, civil engineers, cannot understand the physical meaning of shear center. I thought about it, and from my point of view, the equivalent cross section was the explanation, the real explanation of the shear center. So shear center is actually the centroid of the equivalent cross section. For some cross sections, here the shear center is at the outside of the cross section. For some cross sections, for example, for this cross section, it has no vertical symmetry, and its shear center is inside, not at the outside of the shape. Using this condition, one can found the place OD, which is the shear center, if someone using integration calculates FW1 and FW2, and if someone knows from the geometry of the cross section the distance E1 plus E2, one can find the place of the values of E1 and E2 using this condition. The twisting moment about point D is 0. Okay. But another person can think in this condition, okay, if the shear center lies outside the cross section, using mirroring technique, I can see the shape of the equivalent cross section. But if the shear center lies at the inside of the section, you will again use the mirroring technique. Here you see, now you see this section is here, the hatched section, and the vertical axis, which is the vertical symmetry axis of the equivalent section, and then this hatched shape is mirrored according to this vertical symmetry axis, and then we obtain that portion. So as you see, there are two sections and they are overlapped to each other. Here one overlap you see, here one overlap you see. So two overlapped sections, they are overlapped not completely but at some places, considered equivalent cross section. This is the explanation, physical explanation of shear center. Actually, shear center is the centroid of the equivalent cross section. So the mathematics and the physical understanding of the shear section is given to my civil engineering colleagues. Thank you. Please do not forget to subscribe to my channel. This PDF document will also be provided in my website. I will put it later.